So let's do a sample problem. So 100 milliliters of saline solution, so that's the stuff they give you at the doctor's office or at the hospital, which is, so standard saline solution is 0.92% sodium chloride by mass. It's mixed with 250 milliliters of pure water at 37.0 degrees Celsius, human body temperature. What is the osmotic pressure of the solution? Okay. And so why is this important? For one, if you've ever been on an IV saline drip, you note that they hold it way up high, right? That is to prevent your own blood from coming back up the tube via osmosis. So you have to have that saline drip really high to get the osmotic pressure to pump it through your veins, okay? Which is kind of cool. So let's see here. So we're going to assume, so we need to know the density of the solution. Again, I'm going to assume 1.02 grams per milliliter. And you know, you could be given a solution or given a density if on a homework problem or something like that. And so the first thing that I want to do is calculate my molarity of just this saline solution. Okay, so I'm going to start by saying 1.02 gram of the solution per milliliter. Okay, and I'm going to do the trick where I also assume that I have 100 grams. So if I have 100 grams of this solution and it's 0.92% by mass, then I have 0.92 grams of the solution. Okay? Or excuse me, I have 0.29 grams of not the solution, but rather 0.92 grams of NaCl. Okay? And now that allows me to say 58.46 grams of NaCl in 1 mole. And then now finally I've got the milliliter unit over here. I can say in 1,000 milliliters, there's 1 liter. And so if I now calculate the molarity of my standard saline solution, that's 0.102 times 0.92 divided by 100 divided by 58.46 and then times 1,000, and that's about right, about 0.16, we'll say 0.161 molarity. Okay, so now, but look how this reads. So 100 mils of saline solution is mixed with 250 mils of water. So it's been diluted. And so this is also some nice review. We have to remember M1V1 equals M2V2 because I have to have the molarity of the diluted solution. Okay, so I'm going to solve for M2, and I'm going to say that's M1 times V1 divided by V2. Okay, so my M1 is 0.161 molar. My V1 is the 100 milliliters. And my V2 is now 350 milliliters because I have to remember I'm making a new solution. I've taken the 250 and I'm adding it to 100 to make my new volume of 350 milliliters. Okay? And so let's see, when I do that, I get 0.161 times 100 times, or excuse me, I said times 350. Let's try that again. So 0.161 times 100 divided by 350, yes, 0.0460 molar. So finally now doing the osmotic pressure is pretty simple. It's the Van Hoff factor, I. For sodium chloride, we can assume 2. That's fine. The molarity is 0.0460 mole per liter. The gas constant R is 0.8206 liter ATM per mole Kelvin. And then we're doing this at 37 degrees Celsius, so we've got to convert that to Kelvin. So 37 plus 273 is 310 Kelvin. Okay? And so now I can multiply all these things through. So 310 times 0.08206 times 0.046 times 2. And I get an osmotic pressure for diluted standard saline solution of 2.34 ATM. So that's pretty significant, right? That's a pretty significant osmotic pressure, a pretty significant pressure you would need to apply to prevent backflow. Okay? So the last thing that I'm going to talk about, just very, very briefly, is reverse osmosis. And this is a process in which the solvent is forced through a semipermeable membrane, leaving a more concentrated solution behind. So which is the opposite of regular osmosis. So for example, in reverse osmosis, you typically have these hollow fibers that make up your semi-impermeable membrane. And this allows water molecules to flow through the semi-impermeable membrane, but prevents the ions from doing so. And so the application of this is desalination and water purification. And so the reason I bring that up is because as we move forward in the 21st century with climate change, we're going to have to figure out how to do this on a much bigger scale, especially in Southern California, okay? And for those of you that live in San Diego, you actually may be aware that there's quite a large reverse osmosis water desalination plant there already. As it turns out, the Middle East, so Saudi Arabia, Kuwait, etc., they're really like worldwide leaders in this effort for water desalination. We're going to run out of fresh water if we don't figure this out. And there's actually a lot of folks at HSU that are working on this stuff in the environmental engineering program, which is pretty cool. Okay, folks, so I'm going to leave it there. That's it for my content. I'm going to record one final video as like a saying goodbye and kind of wrapping things up and giving you my final thoughts on things. But this is our last video for content. Okay, folks. Hasta luego.